Hello, everyone. Good morning and good evening. My name is Mike Poulter, and I'd like to welcome you to SPI Laser's webinar on nanosecond pulsed fiber lasers for cleaning and surface functionalization. Hopefully you can see my slides and hear me clearly. Let me know via the chat function if there are any issues you see. So here's what I'd like to cover today. The intent really of this webinar is to provide you with a general overall view of our capabilities in this area, to give you an idea of the scope of the application space, rather than a detailed scientific presentation. I'm going to start with a brief introduction. I promise this will be a brief introduction of SPI Lasers as a company, the kind of products and services that we offer. I'll swiftly move on to talk about laser cleaning, starting with the key characteristics of the SPI nanosecond pulse fiber lasers for this application, before going on to more detail around different types of laser cleaning applications. I'm then going to follow with a section on surface functionalization, again using our nanosecond pulse fiber lasers, and going to some detail on the applications that we are currently using our lasers for in this area. I'll finish with a wrap-up and summary. Please feel free to submit any questions using the question function of the GoTo that you're using today. I will try to address these at the end of the presentation. If I can't address them at the end of this presentation or run out of time, I will be sure to follow these up individually with yourselves. So if we move on swiftly to the first section, just a brief introduction of what we do here. So SPI Lasers has a real core competence in the research, development, production and service of fiber laser technology. We have manufacturing sites in the UK and also a global presence across the world in terms of sales and service of this technology. In addition to this, we also have significant expertise in the development of laser materials processing, with application laboratories situated across the globe. As you can see, we have some in the UK, China, the US, and Korea, among others. This really enables us to provide our customers with innovative laser processing solutions so that they can implement them at the system level. SPI Lasers really offer two ranges of products in terms of fiber lasers. The first is the pulsed fiber lasers. It's really a subject of our talk today on cleaning and surface functionalization. We also offer CW lasers going to much higher average powers. These product ranges really support the huge demand for fiber laser technology that we've seen in recent years, and it continues to replace traditional techniques and other laser types in many areas of materials processing due to the benefits shown here. Just briefly talking about our CW portfolio. Our CW portfolio starts at low to medium power range, from 100 watts all the way to 2 kilowatts. These lasers are available in both air and water-cooled platforms. They're available also in single mode and multi-mode beam options, and have applications ranging from fine cutting to additive manufacturing. The CW product range also extends to higher average powers with multi-kilowatt output, all the way up to 10 kilowatts and soon 20 kilowatts output power, for applications such as large section cutting and welding. Today we're really here to talk about the pulse portfolio, the pulsed nanosecond pulse fiber lasers that we produce here at SPI. Historically, these lasers have been used at low average powers for things like marking and thin section materials processing. But now as we move to higher average powers and high peak powers, we open up new application space, including cleaning and surface functionalization, which is our subject of our webinar today. So if we now move on to laser cleaning as a subject, and start off with some key characteristics of the SPI red energy nanosecond pulse fiber laser. For those of you who aren't familiar with the red energy G4 fiber laser, it is offered at 1 wavelength, currently 1 micron, in powers from 20 watts to 250 watts and increasing continuously. We offer pulse energies in excess of 5 millijoules and pulse durations which are tunable. I go on to talk about a lot more about this in this presentation, but tunable pulse durations from 3 nanoseconds all the way to 2000 nanoseconds, that's 2 microseconds. That's 3 orders of magnitude variation and control in pulse duration from the same source. This also offers high peak powers up to 50 kilowatts within any given pulse and really high pulse repetition frequency, all the way from single shot to 4 megahertz pulse repetition frequency. We also offer CW mode with modulation to give longer pulses where required. This is a key slide for this and many other applications. It shows the output of a typical output of our G4 fiber laser. The key here is to note that the pulse is not actually Gaussian in shape, in time. It has more of a peak at the start and what we call a long tail. This is characteristic of the way we produce the light within our lasers and the fact that we employ our directly modulated seed master oscillator power amplifier technology. This pulse shape is ideal for cleaning applications, among others. And the reason for this is that the peak power or any threshold in peak power for ablation are quickly reached. This reduces the waste energy and limits the excess heating of the substrate and surrounding heat affected zone. You can see there, if you imagine a threshold halfway up, we're meeting that threshold much more quickly within the nanosecond pulse. What the G4 laser offers is huge controllability and flexibility in the control of these parameters. Key variables being pulse duration, pulse energy, repetition frequency, peak power, average power, and beam quality. I'll go on to talk about this in a little bit more detail. But all of our lasers, all of our pulsed nanosecond lasers, offer huge levels of controllability in these variables. One thing that comes out of this is the ability to tailor the delivery of the input energy over short duration. This is key for lots of applications, including cleaning and surface functionality. You can see in this slide, for example, SPI nanosecond lasers are capable of delivering both high and low peak power, but crucially are able to do this both at low and high pulse repetition frequency. Many other lasers, like historic and traditional Q-switch lasers, at high pulse repetition frequency, you not only get lower energy, but you also get longer pulses, and therefore the peak power drops non-linearly with pulse repetition frequency. By using our pulse tune functionality that are built into all of our SPI nanosecond fiber lasers, you're actually able to maintain high peak powers even at high pulse repetition frequencies. This is really key to optimizing many different applications, including cleaning and surface functionalization. Adding to the flexibility of our nanosecond fiber laser sources are the options for different beam quality. Here you can see the 5 different options we offer for beam quality, with M squared ranging from single mode, M squared less than 1.3 or very close to 1, right the way up to 5 times the fraction limited. The thing to note here is that with higher M squared comes higher energy, higher pulse energy, and higher peak power. This really provides another lever to pull when optimizing for a given application, whether it be cleaning, surface functionalization, or anything else. So, laser cleaning. What do we mean by laser cleaning? It sounds like a silly question, but actually laser cleaning could mean a number of things. What I'm proposing as a definition here, at least what I'm proposing to talk about in the context of the slides that are to follow, is really, when we talk about laser cleaning, we're talking about the removal of a layer from an underlying substrate without significant damage to the substrate itself. What are the alternative processes? Clearly, we've been cleaning for a long time. It's not a new process in itself. Existing processes include chemical or dry ice processes. These, however, are not considered to be environmentally friendly. They can involve hazardous materials and also have come with a high cost of consumables and waste disposal. Similarly, if we use sand, grit, or even bead blasting technologies, these can be very dirty and noisy and also come with issues around waste disposal. Alternatively, we could use mechanical styles of techniques in cleaning, involving brushes or other techniques. Again, these are noisy and have a high level of consumable wear. So why laser cleaning? Above the pre-mentioned techniques, laser cleaning really offers a precise and reproducible benefit. We usually combine the laser with a galvo scanner to provide a rastered line that we sweep across the surface at focus. It can be handheld, like the pictures you see in the slide, but actually it can also be installed onto an XY stage, for example, or even mounted onto a robot arm. What this means is that it's not only precise and reproducible, we get limited substrate wear due to the controllability of the energy that is imparted to the layer and the substrate. It can also be easily automated or remotely performed. This is of interest, for example, in the nuclear decommissioning industry, where people can't physically go in to the places that need cleaning. It's also scalable. Lasers can be used to clean very, very small objects and also be scaled to very large surface areas. There's also less waste material, with really only the layer that's removed needing to be managed. All in all, this really means that the laser is seen as a more environmentally friendly process. So if we look at a little bit more detail here at the mechanisms behind laser cleaning.
Hello.
In the ideal situation, the laser beams would be well absorbed in whatever you're trying to remove from the surface of the substrate. Therefore, we need to consider important things like the wavelength. Clearly, the color of the light that we use is key to the absorption in the layer. But also, on top of that, we adjust beam parameters, including beam profile, pulse energy, pulse duration, and peak power, as previously mentioned, to optimize removal of a surface layer. What's interesting is that depending on the substrate and depending on the layer that you're trying to remove, the process can be self-stopping. That is to say, once the layer is removed, no further processing is done, which is not the case, for example, in some other techniques. The physical processes that we're really seeing at the micro level here are ablation, evaporation, melt ejection, and melting. So we're not only just absorbing in layers to remove them by ablation, but we're also using other principles like vapor pressure and things like that to physically remove layers from surfaces using the laser and the energy imparted by it. Here's an example that people, at least in the public domain, would possibly see more often is architectural cleaning. This is an example where we use the lasers in a handheld process for cleaning of stonework on buildings, statues, and monument restoration. This uses nanosecond pulses and particularly at high repetition frequencies with high peak powers. Again, going back to the benefits that the SPI nanosecond fiber laser offers. All of this is done without damaging the surface below, which means it's ideal for texture surfaces, non-flat surfaces, and also surfaces that are precious, such as artwork. However, looking more industrially, we come across some key application spaces in cleaning, particularly around the removal of anodized layers or paint. This is a major application that is commercially of interest. However, this is a general slide before we go on to talk in a little bit more detail about the considerations that are needed when trying to optimize for removal of anodized or paint layers, or indeed any layer when you're cleaning. And that is to say that all layers are not equal. The key attributes of the layer itself include obviously the thickness of the layer you're trying to remove, the composition of whatever it is, the material you're trying to remove, particularly the chemical composition. Could also be the texture and surface quality of the surface you're trying to clean, the color, because that affects absorption. However, note also that we don't always need absorption, at least in the layer itself. We can remove, for example, clear layers that are transparent to the laser by using what we call a lift-off process, whereby the laser will be transmitted through the layer and then actually, due to the interaction of the light at the substrate and layer surface, will actually remove the layer from behind. All of these things significantly impact on the processing speed and quality, so must be considered when we're trying to optimize for this particular application. Staying with paint removal, this is an example of where we have used one of our nanosecond pulsed fiber lasers and the pulse tune technology to change the waveform, so change the pulse energy, change the peak power, change the pulse duration, to selectively remove paint with high speed and high quality. This is an example where we have a thin metal plate which has been powder coated with yellow paint and then red, and individually we've then selectively removed those layers to create an image. And you can see the level of control that you get in terms of depth, where you can remove the red, leaving the yellow, and remove the yellow back down to the metal surface. And then we've used the same source to actually white mark the metal surface below. This is an example whereby we've coated aluminium with electrically isolating paint, and we need to remove sections of this paint to enable us to make electrical contact zones. What we've used here is a 70 watt HSH laser, one of our 70 watt nanosecond pulse lasers with 3 times diffraction limited beam. This happens to be around 2 millijoules pulse energy. What's important in this slide to note is that actually we can use multi-pass strategies to optimize quality and speed. So in this instance, it's actually 3 passes rather than try to remove the whole layer with a single pass, which is actually possible to get the best speed and quality. What we're actually finding is that you can do an initial pass to do a coarse removal of the bulk paint, a secondary pass which uses low energy, high rep rate pulses to clean and remove the residue, and then a third pass, which is actually, it's optional, but it really polishes the surface up and gets to the best finish. And what we're doing here, each one of those passes are using entirely different pulse energies, peak powers, and pulse durations, and it's all from the same laser source. Here's a slide where we have looked at comparing different lasers for paint removal. In this instance, we're removing a 70 by 70 millimeter square area of paint from steel, and we're looking at the different lasers that we offer. I mentioned earlier that we offer different beam qualities which come with different pulse energies and peak powers. Here we call them Z, H, and M. Z being a good beam quality with 1 millijoule pulse and up to 10 kilowatts peak power, all the way to an M, which is 5 times diffraction limited, 5 times the pulse energy, 5 times the peak power, but 5 times the spot size. And you can see here that we get, as we go from the Z to the M, we get an increase in the removal rate of the paint from the substrate. But also what's interesting is we also get a higher removal rate per watt as we go to higher average powers. The M-type laser is a 200 watt laser, average power, operating at 50 kilowatts peak power. And we think this is likely due to an accumulated heating effect, which comes with the higher average power. So that's paint removal. Now we move on to rust removal, another very large application space for cleaning, laser cleaning. We see quite a lot of demand in this area. Laser cleaning is one of the most efficient and effective methods of removing rust now that we're moving to higher and higher average powers. Rust is typically an oxide layer that's formed on the surface of metals. Now, just be aware here that these images show iron and steel, but actually it's just as applicable to other metals like copper and aluminium, which form their own oxide layers also. The important thing to note here, slightly different to paint removal, is that rust manifests in a different way, obviously, to a paint layer or an anodized layer. Effectively, the removal rate of rust can vary significantly depending on the type of rust, which does vary, and the level of corrosion present. You can see here, for example, we have three levels of corrosion. One which is a surface level of corrosion, same substrate, same rust material, all the way to a level 3 where you have not only pitting but deep penetration into the substrate of the oxide layer. What this means is that there are actually two completely different types of laser cleaning processes that are needed to clean these types of materials. The first, really for level 1 corrosion here, is the removal of a layer from the surface of the material. What's interesting is the best setup for that in terms of laser parameters is actually low pulse energy, high pulse repetition frequency, and a high m². Large beams, low pulse energy, but still significantly enough peak power to remove the oxide layer. Interestingly, and completely conversely to this, is that as you go to level 3, a much higher level of corrosion, a much deeper level of penetration, then you actually have to start removing the layer, a very small part of the substrate itself, which can be much more difficult than the oxide. You're effectively engraving the upper section of the substrate material here. What that means is that instead of having low energy, high PRF, we're now using a high pulse energy, low PRF, and low m², so high beam quality. So again, we're using a completely different setup, but effectively removing the same oxide from the same substrate. So you have to be very careful whether you're trying to remove thick rust with high corrosion level or thin rust with a low level of corrosion. And obviously the SPI nanosecond fiber lasers offer the flexibility to do all of this. In this slide, we compare the same lasers again with rust removal. This is just a small subset of the lasers that we offer in the range, but gives you an idea of how things change with beam parameters and pulse characteristics. What we've done here is we've looked at both thick and thin rust. We've tried lasers that are high beam quality, lower pulse energy, lower peak power, and lasers that are higher m², higher peak power, and higher pulse energy. Again, showing that the different pulse characteristics are needed for thin and thick rust. But you can see obviously there that the removal rates increase as we go up in average power and peak power and pulse energy. Another application in terms of laser cleaning is the cleaning of rubber from rubber molds. This particular picture, some of you may recognize it. It's actually to create telephone buttons, rubber telephone buttons. This is really a situation where, when used many, many times, there is a residual buildup of rubber deposit on the molds, which makes the mold different over time, and they need to be cleaned. Again, these can be quite small. They can actually also be quite large also. Imagine the mold of for a car, an automotive tire, for example. Same principle. Our lasers can be used to clean these. The idea is to remove the surface debris and the contamination without damaging the substrate and the mold below, because it has to be reused. In this particular application, because it's quite small, you don't really need high peak power. In this case, we've used a 20-watt fiber laser, one of our 20-watt HSL lasers at 500 kilohertz pulse repetition frequency to do a good job of this. A similar application whereby you see a buildup of material is when cleaning print rollers. This is an example where we use analox rollers in flexographic printing techniques, printing presses. These need to deliver a precise amount of ink, and they have very small pits that are actually made by lasers and laser engraving, which we also do. And these little pits are designed to hold ink, but over time, residue ink builds up, and you end up getting smaller and smaller cells. What that means is that the print quality then reduces with time. You need to then go and clean those. We can do this using our lasers, and in this case, we have 4 40-watt lasers cleaning individually a very large analox print roller. These can be combined onto one system to achieve cleaning speeds of up to 2.5 square meters per hour. Moving on to slightly different cleaning application here is the combination of cleaning with other processes. In this case, we've combined cleaning with engraving. This is an example of VIN marking. This is vehicle identification number marking. This is chassis numbers on cars. Historically done in other ways with dot peen and things like that. We're now doing them very efficiently, very fast, and very effectively with lasers. However, you can see here, using the same laser that we're using to actually engrave the digits into the chassis. In this case, is a 200-watt EPM laser. Moving it around about half a second per character, with one set of pulse characteristics, that is energy, peak power, and pulse duration. And then what we're doing is very, very quickly following that with an entirely different set of pulses and pulse characteristics to clean the engrave that's been done, to give a better contrast and better definition of the text. Again, you can see here that we actually reduced the average power. We took the pulse duration down from 500 nanoseconds to 40 nanoseconds and reduced the pulse energy. And we could do a cleaning pass on top of the engrave. This is an example of where we have again combined laser cleaning with another laser application. In this case, it's not engraving, it's welding. What we're doing here is we're removing a galvanic layer from the surface of steel before, in preparation for welding to other steel parts. In this case, we're using again the 200-watt EPM laser, and we are achieving process rates of greater than 100 millimeters square per second removal of the zinc oxide in this case, to reveal the bare metal beneath, ready for seam welding. What's interesting is that, sticking with welding, in order to prepare for the weld, we've used the laser, and the same laser can also be used post-weld to clean the weld up. Once the weld has been done, we can remove surface oxides and minor spattering using exactly the same laser. Here's another example where we have used the 200 watt EPM laser. Again, the 200 watt EPM is a laser that delivers 200 watts average power, 50 kilowatts peak power, pulse durations from sub 10 nanoseconds right the way up to 2000 nanoseconds pulse duration, and 5 millijoules maximum pulse energy. This is where we've used it to clean back to bare metal on a part that has been thermally discolored. Imagine something like a heat shield, something like that, where it has had buildup of a residue over time due to the heat, and we've cleaned that back to the bare metal. This is an example, a close-up of some cleaning of splines of a drive shaft that we've also done. This could be buildup of oxides. It could be also buildup of oil, depending, or grease, depending on the application. In this case, not only are we removing the contaminants from the machine splines, but also we're not changing the position of the height of this part with respect to the laser. So really this shows that because you're getting cleaning both at the top of the splines and the bottom of the splines, these are about 1 millimeter in terms of top to bottom depth. Shows that it's not really critically sensitive to focus position, and indeed that's one of the reasons why you can handhold these some of these devices for cleaning applications. This is a very popular application for laser cleaning right now. It rides on the back of the demand for battery applications, and also e-mobility, electric cars, and the advent of those. In this case, we are using the laser to selectively remove coatings from battery foils. Now, the batteries really have two types of foil. They have an anode, obviously, and a cathode. One is copper, one is aluminium, typically. They're actually quite thin foils. The coating on them is actually larger, thicker than the foil itself. But what we're able to do by imparting and controlling the energy using nanosecond pulses is selectively remove parts of the coating from the foil that allows electrical contacts to be made. What's interesting here is that the parameters are different depending on whether or not which coating is used, the thickness of the coating, and obviously what the material is on the coating, which depends on whether it's the anode or the cathode. But we're doing these things very quickly, within a fraction of a second to a few seconds. The important thing here is to have minimum burr, minimum heat affected zone, because these foils will be used in batteries, and any contaminants, any sharp edges are not good news inside of a battery cell. Staying with e-mobility a little bit, again, we see other cleaning applications in this application space. In this case, we are talking about hairpins. Hairpins are components within electric motors. Many of them are used within an electric motor, and the idea is that you need to first of all coat them with an electrically isolating lacquer or layer. However, you then have to remove part of that at the tip in order to weld these hairpins together. In order to do that, we can use our nanosecond pulse fiber lasers. Typically, there are 3 common insulator materials that are used to coat these hairpins: PAI, PI, and PEEK. They come in various different wire geometries and various different types of shapes and sizes. What's really interesting here, though, is that depending on which insulating material you're trying to remove, you actually need a different laser or different laser characteristics. For example, for PAI and peak, what we actually see is our 200 watt EPM laser. This is the laser which is higher M squared, higher energy, higher peak power, is great for removing PAI and peak up to 250 millimeters squared per second ablation rates. However, actually when it comes to PI, although the EPM can be used, our EPZ laser, which is actually a better beam quality with slightly lower pulse energy and slightly lower peak power, but higher fluence and irradiance, that's watts per square centimeter, is actually better for removing PI compared to the EPM. Just shows you again that different beam and pulse characteristics are important when considering the application and the layer that is to be removed. Now, a lot of lasers are being proposed for this application. We see IR, so 1 micron wavelength, as being ideal for this because it doesn't affect the copper surface underneath significantly like green lasers may. It also doesn't leave any burnt residue like longer wavelengths, for example, from CO2 lasers. And it's a pretty cost-effective process. And this is being picked up within the industry right now. Just note that the process times are dependent on the material and the thickness coating there. Another interesting application is the cleaning of composite material. This is composite fiber, fiberglass. What we've done here, and this is really interesting, what we've done here, we have removed the polymer material whilst not damaging the layers of carbon fiber. Doesn't have to be high power. This is done using one of our 20 watt lasers, but we're really optimizing the pulse tune characteristics in order to do this. It takes quite a long time, but what this enables is the strong joining of separate parts. Using this cleaned section, we can then join other composite parts to this by applying resin again back in its place and creating a very strong join. Something that's been around for a while, but thought I'd bring it up, is the removal of transparent electrically conductive layers on glass for display panel production, in this case indium tin oxide. Here we are creating very, very narrow lines, very small spots, without damaging the substrate below. And we're able to go pretty quick here, up to in excess of a meter per second. And all we need for this is a 20 watt laser. Similarly, we can remove similar layers, again, electrically conductive transparent layers on glass, but larger areas, using an entirely different laser. So instead of now really using a 20 watt laser with very small spot sizes to create scribes, now what we're doing is we're removing large areas, particularly it's really for edge deletion around the edges of display panels, to electrically isolate from frames and housings of televisions. Using a much higher power laser in this case, 200 watt laser, again the EPM, much bigger spot, higher pulse energy, and we're able to remove significant rates here, almost 20 centimeters squared per second, with no damage to the substrate material. So clearly, as we go to higher and higher average powers, maintaining peak powers that we see with nanosecond pulses, we can go faster and faster. For applications that require the highest speed or the lowest cycle times, or cleaning of the very largest of areas, people talk about cleaning hulls of ships and stripping paint from large jumbo jets. In order to do that, you need to go to kilowatt level average power. Although we currently don't offer this at SPI, our colleagues at Trump offer the True Micro Series 7000, which goes up to 2 kilowatts average power in the nanosecond range. So that's really it for laser cleaning. As I said, this is really to give you an idea of the range and scope of the applications within cleaning that we are currently looking at. It's not exhaustive. We have more. If you're interested, please get in contact. What I'd like to do now is move on to talk a little bit about surface functionalization, again using our nanosecond fiber lasers. The first thing really I'd like to discuss is laser polishing. So we can use even CW lasers, in fact, to polish materials by creating a melt pool and trying to form a smooth remelt layer. However, this doesn't give very smooth and polished finish. In order to get very smooth polished finish, it's really necessary to go down to what we call laser microprocessing, where the pulse laser comes in. By doing this, we again remelt, but just on a much smaller scale. What we're able to do in this case is get to a remelting depth in the order of microns, which gives a much smoother surface with RA at sub-micron level in some cases. Normally, this is a two-stage process. Depending on the original state of the metal, you may have to do a macro polishing process and then follow it with a micro polishing process. This is an example where we have, in this picture, courtesy of our friends at Heriot-Watt, are polishing on stainless steel with one of our lasers, again using a combined process of melting and micro polishing. Applications for this include the cleaning and polishing of tools, dies, molds, implants, surgical implants that is, also for fluid flow applications and fluid dynamics. It's important here to optimize, again, just like it was in cleaning, the beam and the pulse characteristics to get a completely flat and polished surface. It's actually really difficult to do that, not impossible, but it's difficult to do, and that's why it's important to flex those parameters to optimize the process. This is an example, again, of polishing on aluminium rather than steel. In this case, we've used a 200-watt laser with a long pulse, highest energy, longest pulses. We're using high repetition frequency. In this case, in a single pass, but sometimes things can be improved by multi-passing. It's high speed with processing of greater than 1 centimeter per second, and the resultant RA, like I say, can get down to sub-micron. That's surface roughness. Something else we're doing with surface functionalization on our lasers is reducing friction. This is usually done using ultra-fast lasers to create microstructures, but actually we can do this also with our nanosecond lasers to some extent. This is an example of whereby we are creating lubricant reservoirs or hydrodynamic bearings, or reducing just surface contact, in fact, between surfaces. And in some cases, we can reduce the coefficients of friction by as much as 80%. Really, this is looking at producing surface structures and dimples within the surface itself. Conversely, we can increase friction also. Again, this is something that a lot of people talk about with ultrafast lasers. When we talk about surface functionalization generally, it usually turns very quickly to ultrafast sources, that's picosecond and femtosecond sources. However, what's interesting is that we've been able to show that for some, not all, but for some applications, we can actually adapt nanosecond pulses to create the same or very similar effects in some cases. This is a perfect example where we are using nanosecond pulses rather than to create very controlled microstructures, which we would with a micromachining laser, a femtosecond or a picosecond laser. We're emulating those structures with a nanosecond pulse. In this case, we are doing a design of experiments that show the effect of pulse energy and overlapping and pulse overlap on the surface structure, as you can see there at the micro scale. This is really interesting because it shows that we can really significantly, in some cases, increase the coefficient of friction. As you can see here, almost by a factor of 5, increase in the coefficient of friction for this particular application. Using similar methods of creating those features with the nanosecond pulse laser at the micron level, we can not only control coefficients of friction, but we can also control coefficients of heat transfer. This is an example where someone has been using our lasers, one of our lasers, to texture surfaces in order to increase the nucleate boiling heat transfer coefficient to water, and also binary mixtures of water and alcohol. This is used in distillation, petrochemistry, refrigeration, and even nuclear power generation. And you can see there from the graph on the right that the coefficient of heat transfer from a solid hot surface to the liquid being heated and boiled can increase significantly. Again, factors of 4, 5, 6 even or more in some cases. We can't really talk about surface functionalization without discussing wettability. The wettability of a surface, the readiness of a surface to accept or repel water, in particular, or liquid, depends on a number of things. This is quite a large field when it comes to surface functionalization. But really what we're interested here in the nanostructure and the microstructure of the particular surface as it is in contact with water droplets or the water itself. There's also surface chemistry that's involved. It's not just about the geometric structure of the surface. There is a level of surface chemistry and physics that is involved in this also. So we're able to use our nanosecond lasers, which some people may think is not possible, but we are able to use our nanosecond lasers, not picoseconds or femtoseconds, to create the kinds of conditions that are needed for both hydrophobic and hydrophilic applications. In this case, we can process surfaces to be hydrophobic, and then after a post-processing application, which is either a waiting time in some environment or some thermal heat treatment, for example, can make the surface highly hydrophilic. So how do we really control this? Again, this is an example of where someone's been using our nanosecond lasers to create microstructures, again in the same way as you would with an ultrafast laser, but using a nanosecond laser. So not really cold processing in this case, but emulating the kind of conditions that you would get when cold processing. And in this case, you can see that initially the surfaces, as you'd expect, are highly hydrophilic. But after a time, once they've gone through a prolonged environment for, in this case, a number of days, you can see it becomes actually highly hydrophilic. In this case, we're creating contact angles that are in excess of 155 degrees on this particular surface, and a roughness of around 10 microns. You probably can get a smoother surface from an ultrafast laser, but just bear in mind that ultrafast lasers are typically, factors maybe 5 to 10 times the cost of a nanosecond laser. So here's an example just to finish, a little bit of fun to show you a GIF of our hydrophobicity on aluminium. This is an aluminium plate that has been processed with a nanosecond fiber laser. No other coatings, just processed with the laser. and that is creating a hydrophilic surface. On the very same material and on the very same surface, in fact, the other side of this part, we can then create a hydrophobic surface. You can see here, hopefully, the GIF is working once it's got to you guys. In this case, you can see that on, again, this is aluminium plate. We've processed this with a nanosecond fiber laser, and again, no post-processing other than the required weight in the right environment in time. And what we're achieving here is high contact angles for hydrophobicity. So that really brings us to the end of our webinar. I'd like to wrap up very quickly and take some questions for those who have any. Again, if I don't address the questions now, I will be sure to address them by email afterwards. So in summary, the range of nanosecond fiber lasers that SPI offers are ideally suited to the varied requirements of laser cleaning. They can also be used for numerous applications that benefit from surface functionalization, to the contrary of some opinion whereby an ultrafast laser is always required. It is important, however, for both surface functionalization and for surface cleaning that the laser beam quality and the pulse characteristics are tuned in order to get the optimum effect and optimized performance, whether it be speed, quality, or both. The SPI red energy nanosecond fiber lasers offer a huge controllability and flexibility in temporal pulse shaping, control over pulse energy, pulse duration, and peak power. But also we offer different beam characteristics in the spatial domain that gives you another lever to control quality and process rates. So thank you very much for your attention. I'm going to move on to some questions here. Just bear with me. Okay. So I have one question here, which is, can CW and QCW lasers also be used for cleaning? So the answer to that is yes, in some circumstances. However, just bear in mind that they clearly won't have the levels of controllability in the characteristics that I've discussed throughout this webinar in terms of peak power, in terms of pulse duration, in terms of pulse energy. That will enable you to deliver the energy to the surface with the control that a nanosecond pulse laser would provide. You can use CW and QCW in some applications, but if you're not careful, because of that non-controlled or lack of control in the energy and power to the surface, you can end up with burning and charring rather than clean removal of the surface layers. There's another question here about heat. How much heat goes into the substrate material during the cleaning process? Well, this really depends on the application, obviously. One particular application that I showed during the webinar is the battery foil example. That's a great example because, as I said, the foil is actually much thinner than the coating you're actually removing. Sometimes by a factor of 4 or 5, and we're able to remove the coating without damaging the foil beneath. And again, this comes down to really careful consideration of the pulse characteristics to not give too much energy, just enough to remove, but not too much to damage the substrate below. Here's another one. What happens to the material that is removed during the cleaning process? Can it be hazardous? Well, obviously it depends on the material that you're removing. But yes, sometimes I think I mentioned the nuclear waste industry and decommissioning of nuclear power plants. Clearly, lasers are used for this application as an example, whereby a surface is removed and is clearly radioactive. Sometimes it can be hazardous, sometimes it can be toxic. What you need to make sure of here is that you're using the correct extraction. It's just like any other laser process whereby you would need to create or provide fume extraction and the right filtering and management of particulate and gas that is generated during the cleaning process. Final question here. This one is about the this is about the range itself that we offer, and it's about length of fiber delivery. So this is an interesting point. The cleaning applications often require long fiber delivery cables. This is because they don't want to drag the fiber laser around with them, or the laser source and its power supply, in order to clean, particularly for handheld applications. At the moment, we offer up to 5 meters cable lengths, and we are going to be offering much longer cable lengths, up to 10 meters in the very near future, for lasers that will be particularly targeted at cleaning and surface functionalization. So yes, the issue as to why you can't just completely keep increasing the cable, unlike a CW laser, for example, which you often see with tens of meters delivery cable, is because when you go to higher peak powers that you generate with a nanosecond pulse laser, you get nonlinear effects within the fiber itself that limits the operation. Clearly, you need those high peak powers to do the process itself, but in this case, there is a limit to the amount of glass that you can propagate that light through. So we're really limited. But what we're doing at SPI is we're coming up with new ways of trying to maintain that peak power over longer cables to be delivered for these types of applications. Okay, so I think I'll wrap up now. Thank you very much for your attention. The only thing to say is the next webinar that we're due to broadcast from SPI is on cutting and scribing with the same nanosecond pulse fiber lasers that I've been discussing today, and that will be on the 16th of July this year at the same time, 3 p.m. GMT. Thank you very much for your attention, and happy cleaning.